Okay, so while the next speaker gets his slides shared, I'll introduce him. So the next talk is called Implementing Stable Unstable Semantics with ASPTOOLs and Clingo. And the speaker is Tomi Janhunen from Tampere University.
Okay. Apparently you can see my slides now. So and the mic is working since I asked a question. So,
yep.
This is work toward implementing this stable unstable semantics, where we try to solve problems. Well, pretty much in the traditional way, we want to find a solution, but then we have a potentially collection of sub-problems that are not supposed to have solutions. And well, typical example could be like some design problem, and then we want to check that the design is correct. So we want to make sure that there are no counterexamples or misbehaviors for the design. So such problems would perfectly fit to this line of thinking, that there is a stable model, and then we want to check for some further sub-programs that there are no stable models. So the rough outline for my presentation is that I will explain the motivation a bit further, and then the technical side, what is needed for this implementation, and the end of the presentation I will devote that for explaining one practical encoding, how these problems could be solved following this approach. And then I'm ready to conclude. So we have already seen some examples of answer set programs. So I will just briefly summarize that we have the rule-based syntax and the semantics based on stable models. And what is, of course, interesting here is that when we check the existence of answer sets from the complexity perspective, there's distinction between normal programs and disjunctive programs. So when we have proper disjunctions, we can solve problems up to the second level of polynomial time hierarchy. But when we have only normal rules available, then problems are easier and the expressive power of rules is lesser. So in a sense, the approach based on stable, unstable semantics reaches also to the second level of the hierarchy, and even beyond if we apply this idea recursively. So one of the techniques that can be used to encode oracles in this setting when we use disjunctive programs, it's so-called saturation technique that goes back to the original complexity result even. And what is cumbersome with this is that the oracle is effectively encoded in CNF. And sort of we lose the notion of stable models when we program oracles. And well, in spite of this, many problems have been solved using saturation, but nevertheless, there are also some other difficulties at site. So this is just a kind of a very schematic view of a positive rule that we use to encode saturation. And there, the issue is that there are now instances of predicates there. And when we encode the saturation part of the encoding, we should, in a sense, match these rules with the saturating rules. And the grounder is doing a job in between. So making a perfect match is sometimes a headache for the programmer. And debugging these encodings is also tedious. So one of my ideas in this approach is to delegate this saturation part to a separate translator. So a few words about this stable unstable semantics. So rather than using disjunctive programs to program the second level, the idea is to use normal programs and to make these oracles very explicit. And also, basically, they could be just normal programs. And how do we reach the second level is that we then change the mode of reasoning for the oracles. So we insist on instability of the oracles, perhaps given some truth values from the main program. And if we do this recursively, we can reach any level of polynomial time hierarchy. There are related approaches that appear a bit later. They try to make quantification explicit in this approach. So either quantifying over answer sets or individual atoms. But there's a kind of a very clear and intimate connection to stable, unstable semantics from these approaches. And for the moment, the implementation is basically toward translations into QBFs, so quantified Boolean formulae, rather than building a kind of a native system for solving these encodings. In this work, I try to make a step toward native translations and native implementations and basically using existing tools to implement stable, unstable semantics. So the rough idea is that I start from some main program module and the Oracle program modules, and then I translate them into a single disjunctive logic program that we can feed as input for disjunctive solvers. And the catch is basically here that now these oracles here are more or less normal logic programs, and we can use all their features. And basically, although the theory part says that the main program is also a normal program, it's not necessary to constrain that. So we can basically exploit anything that Clingo is offering when we encode the main program. So regarding implementation, we use Clingo for grounding, and the idea is to ground these modules in separation. We put them together, and then we use clasp as the backend solver. But when we do all the intermediate steps, we're exploiting various translators that I've implemented in the past. So first of all, translations toward satisfiability, and then linkers that enable putting these modules together. And the new thing here is basically the saturation transformation, so a dedicated translator that will do the saturation part for us. So let me then explain a bit the technical background toward the implementation before I go into more practical things. So I'm counting basically on disjunctive logic programs here, and I expect that you're already aware of the special cases from the previous presentations. So what is interesting here in particular is having normal rules which form the class of normal programs. So this is a fragment of disjunctive programs, and the idea would now more or less to concentrate on this fragment when we consider this stable, unstable semantics. And well, in general, if we look at disjunctive programs, the program reduct is used as usual. So the idea roughly is that we interpret the negative conditions in the rule bodies with a model candidate, and then we check that the model is indeed a minimal model for the reduced program. And this is the condition for stability. And in case we have these integrated constraints or denials, we also check them by the side, so that this is why we're insisting here that we have a model for the program. So we want also to satisfy all the integrity constraints. And this means also that we can use integrity constraints to select stable models. So this is the standard semantical background, but let's see how stable, unstable semantics is different from that. So there we have, first of all, the main program, and we're interested in some stable model of the main program, be it M here. And then we check for each oracle that when we add certain input facts to the program, after adding those facts, this program becomes inconsistent or incoherent. So there are no stable models for that. And indeed, what we do here is that we are looking at atoms which are in the model candidate, coming from the main program, and which intersect with the signature of the oracle. So these are the facts that are added. Well, here's a very simple example. So the main program is simply about choosing between A and B. So we are getting two model candidates for stable, unstable models. So if we consider M2 first, there's B, which is also in the signature of the oracle here. So we are adding B as a fact to these rules, which means that we are basically canceling these latter rules here, and that is satisfied. So we can see that there's a choice between C and D. So these are the stable models that arise for the oracle. So having one of them is of course enough. So we will say no, this is not, the M2 is not a stable, unstable model in this case. However, if we consider the other alternative where A is true, B is false here, so we're not adding anything. So then basically this rule is not active and the negative conditions here are satisfied. So we're having a loop of three negations here: C if not D, D if not E, E if not C, and that's clearly unstable. And then we can say yes. So this is roughly the idea. So for the main program, we seek for a stable model, and for the oracles, we check for instability. And every oracle must be unstable. So this is already a slight generalization with respect to the original definition where we just employed one oracle. But we can have several oracles in case we want to check several complex conditions given the stable model for the main program. So technically, what I need to establish the soundness of my approach, I employ modularity there. And this is also some previous work where we studied what it means to put program modules together. So roughly, if we put two modules, we join them together, how do we calculate stable models for this combination? So basically, we can calculate the stable models for the component models in separation, and then we join them together. This is very similar to joins in databases. Here I have a very simple example with pi1 and pi2, just single rule per module. These are the output signatures. So this module is defining A and this module is defining B, and the inputs are vice versa. And when we put the modules together, we join we put the output signatures together. So this program is defining both A and B, and all the inputs are met. So the input signature becomes empty. So there's no need to add anything to this program. It's a complete program in that sense. What happens at the level of stable models, we can see that here we have, so now B is an input here, so B can vary classically in a sense. So we are getting two stable models, and similarly here, A can vary. So if we have A true, we will get B true as well. And if it's false, then B is false by default. So we're getting also the empty stable model here. And then we check for compatible pairs of stable models. This is the join operation. And for these two modules, unfortunately, there are no compatible pairs. So the set of stable models for the join is, in this case, empty. So the overall program is inconsistent. It's also easy to see this. So if we have not B, we will get A, and from there we will get B. So there's no way to achieve stability in this case. In this approach, I will also exploit translations from normal programs into satisfiability, and there are several proposals. Personally, I implemented one of the most compact ones, and here I'm just illustrating the one based on loop formulae. And in the worst case, there are exponentially many loop formulas, so then it could be even exponential transformation. But given these three rules, we can define A via this equivalence. So this is Clark completion, basically. And we give the definitions also for the rule bodies. And B has only one rule. We can simply equate that with A. So this is the part that corresponds to Clark's completion. And then, well, we could already calculate classical models for that. And we would obtain supported models for the logic program, the original program. Now there's one important case that we want to exclude. So if there's no external support, so the body of the second rule is false, we can falsify both A and B. Because there's a loop between, so A depends positively on B and B depends positively on A. So then we can calculate, given all the formulas and the clauses, we can calculate the classical models, and we're getting something that corresponds to the stable models of the original program exactly. So there are two stable models for this program under the assumption that C is an input atom, so it is varying, so it can be set either true or false. So this is one instrument for me, and the latter one that is still needed is the translation for saturation. So there the idea is to capture unsatisfiable set of clauses with the existence of a stable model for a disjunctive program. This is the catch. So we're not reducing co-NP hard problem to NP hard problem, but the target is a sigma 2p complete problem. So there's no problem in that sense. So this is simply the illustration. So we have three clauses, and we can turn them into positive disjunctive rules, basically turning them into implications. And in addition to that, we add some new atom U. You could say it reads for unsatisfiability to every head. And then we add saturating rules. So for every non-input atom, so B is input here. So we add a saturating rule. So A needs one. So and then we have the magic rule U. If not U, this enforces the saturation, and we will basically now get only one stable model where B is false. So this is exactly the case where when we falsify B, these two clauses are active, and A and not A should be satisfied simultaneously. So this is clearly inconsistent. So this is how we capture inconsistency in this very simple example. So these are the techniques that I use, and this is the main idea behind my approach. So I map every oracle, I translate that to a satisfied problem. I then apply the second translation for saturation, and putting all together, I get a translation using which I can find stable models for the main module, such that we don't have any stable models for the oracles. Let me still show a few slides about the practical side. So with my earlier colleagues, Bart Bogarts and Shahab Tasharovi, we proposed a very difficult problem of point of no return. And so I'm using this as a kind of a benchmark here. So the idea is that we try to find a path satisfying clauses along the way such that we reach the point of no return from where we can't come back to the start node. So the clauses on the way, if we add them to the clauses that we have seen already, they either make this inconsistent or this is dead end otherwise. So that's the problem. And in the paper, you can find sample encoding. So first of all, small database, which describes a problem instance. So here we have a point of no return. If we go this way and we can satisfy the 3 clauses, but the 4th combination is denied by that. So there's no way to come back here to the start node. So for now, this node is a point of no return. And when we do this modeling, typically we need some domain definitions. So what are literals, what are atoms, the arcs, the nodes, the start node, we can define them as usual as a kind of a domain theory. The domain part, this is something that we can share between the main module and the Oracle module in this case. The main program is simply choosing a path to a point of no return candidate. So it goes through the graph to certain node, and we use reachability here, and then we check that the clauses on the way are satisfied. So the main program gives us a candidate for a point of no return, and the Oracle checks that there are no counterexamples, but since we are using instability here, we can concentrate on modeling the counterexample. So here we are choosing, again, a path that takes us from the point of no return to the start node, such that everything is satisfied along the path picked by the main program and the path picked by the Oracle. And if we have instability, then we exactly capture solutions to this point of no return problem with stable, unstable models. So I did some experimental results. As you can see, the graphs show that this is indeed a demanding problem for CLASP. So this is, we have a linear scaling on logarithmic scale. So this is also supposed to be kind of a challenge for the future solvers to solve these kinds of problems efficiently. So let me finally conclude. So the idea here is that we model problems pretty much using normal logic programs or effectively normal programs, or anything that we can translate into normal programs. And then with this stable, unstable semantics, when we do the translations, we outsource the difficult part, the saturation transformation, for another translator. In this approach, we don't use quantifiers explicitly, so the quantification remains implicit. It's determined by the signatures of the programs, and the implementation will be made available at GitHub. It's already available as binaries at the old ASPTOOLS pages. And as regards future work, there might be ways to improve the SAT encoding from normal programs to SAT. And this is in particular what I'm interested in, so having native implementations of stable, unstable semantics, something like what GND was, but using CDNL solvers to implement the search for stable models and showing that there are no stable models for the oracles. And if we do this systematically, we can basically cover any level of polynomial time hierarchy. So thank you very much for your attention.
Okay, thanks. Thank the speaker however you can. The little hand clapping buttons and things. So we have some time for questions, so please add a question to the Q&A. There is one. Oh, no, wait, that was a previous question. Never mind. So if you have any questions, please, if you're in the room, let the student volunteer know. If you're online, add a question to the chat box or Q&A box. So while we wait and maybe give people a chance to think, I'll ask a possibly very naive question, since this isn't an area I'm very familiar with. In the polynomial hierarchy is also known to be related to various classes of logics, and I'm not sure whether that's there's something called descriptive complexity, which I have a passing familiarity with. Is this mapping between, in this talk, one level, or in general, as you discussed in future work, other levels of the polynomial hierarchy, related to the kinds of characterizations of logical characterizations of these complexity classes in descriptive complexity, or is that not something you're familiar with? Or I don't know if that's really a well-formed question. But
well, of course, certain reductions are, so in the original paper already we show that with the stable unstable semantics we can cover. So applying this idea recursively, we can cover any level of the hierarchy. So certain reductions are implied already from that. Of course, what matters to some extent regarding expressive power here is that how nicely you can encode certain problems, and this point of no return problem illustrates indeed the case where the oracle encodes recursive conditions, and those are quite difficult to express directly as SAT problems. It would be kind of a very, very complex exercise to combine. So to write in hand, do one encoding that combines the SAT encoding and the saturation encoding. This is what I can tell about the relationships roughly. So although these problems map to the same classes of polynomial time hierarchy, there are great differences when it comes to ease of modeling.
Okay, thanks. So I don't see any other questions, so I think we should probably wrap up here since we're now slightly over time, and people at the conference in person may want their lunch. So
okay.
Let's